Okay, so hello everybody. So welcome back to the classes of EE 306. So as you know, we have to continue our lectures online for a while because of the virus break. So this is going to be our first lecture online, so it's going to be a new experience for me as well as for you. So at the end, you can let me know if you liked it or not, or if we have to keep, if you would like us to keep this format or change it. So, okay, so here is how it's going to work. We will go over some lecture notes. Actually, the first thing that you should do to watch this video, before watching this video, would be to go to Ode to Class. So here, this is the page of Ode to Class EE 306. So you go to all sections. And then there you will see the lecture notes. So if you look at the content of this week, March 23, you will see the lecture notes of chapter 3. So this is what you should download first. So you will see a file that looks like this. So actually, this is the format that we used to use in most of the sections, I guess, in EE 230 or EE 301. So it's basically the same idea. So the theoretical content will be here. And then every now and then we will have some blanks to fill in or some exercises, examples to solve. Actually what you should do before watching the videos should be to print this document and then take a pen and paper and then write at the same time as me. So when I solve the questions or when I explain some things, by the way, I will be using this whiteboard, so let's give it a try. Okay, so you will be seeing what I write on this virtual whiteboard, and at the same time you can take your own notes. Okay, so let's give it a try and see how it's going to work out. Alright, so before we begin the lecture of today, let me give you some orientation information. So as you know, my section was section 3, and then there were 2 other sections that were led by Melek Hoca and Arzu Hoca. So what all the sections covered so far was the chapter 1. So basically I'm in the same format as the course syllabus here. So chapter 1 was a review of the theory of random variables and random vectors. So we covered these in class between weeks 1 and 3. Then we started random processes and correlation functions. So these were covered on weeks 4 and 5. And then we started last topic, stationarity and ergodicity. So I guess all the sections covered the content, the content listed in here. So let's remember what we already saw. We saw the concept of first order, second order, and order stationarity in general. We looked at stationarity in the mean, stationarity in the autocorrelation function. If a random process has these 2 properties, we called it wide sense stationary. And finally, we defined stationarity in the strict sense, SSS, and we solved a couple of examples. So this is what has been done in common in all 3 sections up here. So in section 3, this is where we were left. So this we'll start today with the new topic, 2 random processes. And I guess in the other 2 sections, this topic has already been covered in class. So if you're from section 1 or section 2, you can basically skip this part of the lecture. I don't know if you have covered ergodicity. I think some people may have already seen this in class. So if you have seen ergodicity as well in class, then you can skip this video. You can continue with the next one. Otherwise, you can just jump to the point in this video. Hopefully, we will cover both of these subjects today. Okay, so let's give it a start. Alright, so we start with 2 random processes. So the idea here will be, well, you know, so far we have, what have we seen? We have seen a random process x tilde of t. We have defined several properties, the mean function, the autocorrelation function, the autocovariance function, and so on. So what we will do today is we will generalize these topics to 2 random processes. So we will have one x of t, a random process x of t, and another random process y of t. And we will discuss topics like when are these random processes independent, can we define a kind of a joint correlation function or covariance function, and so on. So what we will be basically doing is to will be to characterize the behavior, the joint behavior of these random processes through a couple of random variables. So we will actually, all the definitions we will see in the next couple of pages will be based on these random variables. So we will take time instance, we'll look at the random process at some certain time instance, let's say from t1 to tn for x, and some possibly other time instance t1 prime to tn prime for y tilde of t. And all the definitions will be stated in terms of random variables that we obtain by looking at these random processes at arbitrary time instance. Okay, so the first definition we have is here. So we'd like to first define the independence of our random processes. So as you know, we like making drawings, so let's, oh my god, I have to get used to this virtual whiteboard. Okay. Oops. Okay, so let's try to draw a random process x of t. So here's one realization. If you want, we can draw another realization, and so on. So these are some realizations from x of t. My painting is not that good. Okay, so the way I like showing random processes is I try to draw at least two realizations, and then usually I try to represent a random variable here as this line. So and then we will have another random process y of t in addition to x of t. Now the first definition we need to make is the we would like to define when we can call two random processes independent. So here is another realization for y of t. So let's say that we look at the random process x of t at some time instant t1. So let's pick some t1 in here, and then let's pick some t2 in here. So basically you can think about the random variables x of t when you evaluate at some t1. So you have this random variable x tilde of t1, and then you might have some y tilde of t2. So probably the first way that we might think of in order to define the independence of two random processes might be to say, okay, I will call these two random processes independent when this random variable x of t1 and y of t2 are independent random variables. So that might be a good try. However, the concept of independence actually is stronger than that. So the definition that we will see here is not exactly this, but it's something that's stronger than this and that implies this. So let's see how we define independence of two random processes works as follows. We don't just look at random process at some t1 and t2, or let's call it t1 prime, but it's something stricter than this. So what we do is we look at this the first random process at arbitrarily many different time instances, let's say from t1 to tn, and then take also time instance from the random process y. So look at y at these time instance t1 prime up to tn prime. And then so if you just concatenate these, if you just put them into two random vectors, so you'll have one random vector x and one random vector y. So when do we call two random processes independent? This first random vector x and the second random vector y should be independent random vectors, no matter where you choose this time instance t1 up to tn and also t1 prime up to tn prime. So if you want to go back to the picture, so I'll just change my notation in here. So let's make this one t1 prime. So we have some t1 prime here. And so let's call this t1 prime. Okay, so you look at the first random process at as many time instances you want, t1, t2, up to tn, so many of them possibly. And then secondly, on the random process, you also look at it as many time instances as you want. So it's some t1 prime, t2 prime, and so on. So you have all these random variables. So if you wanna draw a picture of what independence, how independence can be visualized, so all the random variables you see in here should be independent of all the random variables in here. So here's just one detail about how you can characterize this kind of independence. So when you say that this random vector should be independent of that random vector, it means exactly the following actually. You just think about the joint density of these two random vectors. So that will be f of x, y. So x tilde bar and y tilde bar. So this overall joint density should be decomposable in the following form. It should be written as fx times fy. So x meaning the random vector, the first random vector, the joint density of the first random vector times the joint density of the second random vector. So whenever you can write the joint density of two random vectors in this way, then you can say that these two random vectors x and y are independent. And when can you call two random processes independent? You can call them independent if the random vectors x and y that you form in this way are independent for whatever choice of these time instants, t1 up to tn, t1 prime up to tn prime. By the way, it should also be, the statement should be valid for any value of n and m. So you should be able to put as many random variables as you want in this vector and in that vector. So as you see, this is something actually quite strong. So this is stronger than saying that this random variable x evaluated at some t1 and random variable y at some t1 prime are independent. So it's not sufficient to say that this makes these two random processes independent. You should be able to say that for as many combinations of random variables as you want. So this is how we define independence of random processes. Okay, if we continue with the next definition, the cross-correlation function of the random processes x and y. So remember what was the autocorrelation function for a random process x, a single random process. So let's think about a single random process x of t. The autocorrelation function was defined as follows. So Rx of t1 and t2. So we're basically thinking about this random process, and then we thought about the random variables that we obtained by looking at x of t at two different time instances, t1 and t2. And this autocorrelation function was the expected value of the product of these two random variables. So x of t1, x of t2, and in the general case, if x is a complex valued random process, we put a conjugate sign in here. So this was the definition of the autocorrelation function for a single random process x of t. Now, what we have is we have two random processes. So we have one x of t, and we have one y of t, and we would like to generalize this definition. So the notation is actually quite natural. So R is again for autocorrelation function. So you put the name of the first random process and then the name of the second random process. So you have two time instances as before. The autocorrelation function is about two random variables actually, as in the previous case. So you have these two random variables. So the convention is the following. When you see t1 here, it refers to the first random process x. And when you see t2 here, it refers to the second random process. So then you have these two random variables, x evaluated at t1, which gives you your first random variable, and then y evaluated at t2. And the cross-correlation function is about the product of these two random variables. So expectation of the product. However, if you're in a complex setting where x and y could be complex, you put the complex conjugate sign. So this is the direct extension of the autocorrelation function for a single random process to two random processes. So this is called Rx t1 t2 is called autocorrelation function of x, and this Rxy t1 t2 is called the cross correlation function of the random processes x and y. Okay. Now, so you're supposed to be writing this formula in the blank space in here. All right. So the next definition we have is the cross-covariance function of the random processes x and y. So this is also quite simple to extend the concept. What we are trying to do now is to generalize the concept of autocovariance function to the concept of cross-covariance. So again, when we had a single random process x of t, we had cx of t1, t2, and then remember this was nothing but the covariance of the random variables. So let's write it maybe this way: covariance x of t1, x of t2, right? These two random variables. Now we are in the setting with two random processes, so we have x of t and y of t. So we'd like to just take this concept and generalize it for two random processes. So what we call the cross-covariance function is again, notation is the following. So you had a single random variable x in here. Now we have two of them. So we have cxy. And again, we look at this thing we look at these two random processes at two different time instants, t1 and t2. So this cross-covariance function is nothing but the covariance of these two random variables that you obtain by evaluating x of t at this first time instant t1 and then y of t at this second time instant t2. So, and now let's write down this covariance definition. We know what covariance of two random variables is. So I write my first random variable, which is x of t1. So I have to subtract its mean, so I would like to write down the expected value of this, which is the mean function of the first random process evaluated at x1. And now I write my second random variable, so I multiply this with y at t2 minus the expectation of my second random variable, which is the mean function y evaluated at t2. So this is the expectation expression. So in the case where x and y are complex values, you just don't forget to put a complex conjugate sign on the second random process. So this is called the cross-covariance function of the random processes x and y. Okay. Now, well, actually, if we just like to visualize these, what does this really mean intuitively? So this is the picture that you should bring in front of you. So you have a random process x of t. So here's a realization. You might have some other realizations. So you look at this thing at some time instant t1, and then you have a random process y of t. So here's a realization, here's another realization. So you look at the random variable that you obtain. So let's make this clear. Okay, so you look at this random process at some time instant t2. So this first one is a random variable, second one is a random variable. So if we just denote this one with red color and the other one with green color. So what you see here in the first definition is, let's go back to the previous slides. So this function, the cross-correlation function, is nothing but the expectation of the product of these two random variables. So the product of the red random variable and the green random variable. And what we define as a cross-covariance function, as in here, is the covariance of these two random variables. The covariance of the red random variable and the green random variable. So this is how you can visualize this. So of course, as you change the time instance t1 and t2, so if you pick your t1 here or later, or similar if you pick your t2 here or later, depending on where you choose t1 and t2, of course, the correlation or the covariance value changes. So this is why you actually get a two-dimensional function, cxy t1, t2, just like Rx1, T1, T2. They depend on both T1 and T2. So these are, you can imagine these functions as a surface, depending on T1 and T2. Okay. Now, back to the slides. Now you have a couple of similar definitions. So the random processes x of t and y of t are said to be uncorrelated. So remember this. This actually follows very naturally from the definition of correlation for random variables. So when you call two random variables uncorrelated, you call them uncorrelated when their covariance is 0. So it's very similar here. So two random processes are said to be uncorrelated if the covariance, the cross covariance function is identically equal to 0 for all T1 and T2. So let's say, oops. Okay, I want to get rid of the green color now. I'll have a learning curve to get used to this virtual whiteboard thing. So right, back to the line. Okay, what was I saying? So again, I'm uncorrelated. So we say that x of t and y of t are uncorrelated if their covariance is if their cross covariance function is identically equal to 0. For cxy t1 t2 should be equal to 0 for all t1 and t2. So if this is the case, you say that these two random processes are uncorrelated. So no matter where you look at these random variables, no matter where you choose, where are my green and, okay, they're here. So no matter where you choose T1 and T2, these two random variables, the red random variable and the green random variable, they are always uncorrelated. So if this holds, then you say that these two random processes are uncorrelated random processes. Okay. So the next definition we have, okay, by the way, a remark. So you might wonder when these cross-correlation and the cross-covariance functions are, how these two functions are related. So if you just go back to the definition of the cross-covariance function here, just imagine that you're expanding this actually. You have a product here. So, okay, x minus eta x multiplied by y minus eta y. So just imagine that you're expanding this expectation. So let's look at the terms you will have. So x t1 times y star t2 will be, what will that be? It will be the cross correlation function. So it's going to be r xy t1 t2. Remember the definition of r xy t1 t2. So this is what you have. Now the next term you will have will come from the cross term. So expectation of x times eta y star, but this is going to come out as this term actually. So what you have is eta x t1 eta y t2 with a complex conjugate sign. So if you look at the other terms, you will have a third term coming from your eta x times this goes out of the expectation as eta y. So minus 1, it makes minus 2. Last terms, eta x times eta y. So minus 1 makes plus 1. So minus 2 plus 1 gives you minus 1 back. So if you just expand them, sorry if this was confusing. If you just expand this on your own, you will see that the three last terms can be grouped together to give this last term. So this is how the cross correlation and cross covariance functions are related. Here's just one comment about this. So when you know that your random processes are uncorrelated, which means that uncorrelated means the cross covariance function is identically equal to 0, you basically have a situation where this expression is equal to 0. But then when this expression is equal to 0, it means that the cross correlation function is equal to the product of the mean functions, so that you have this identity. The cross correlation function here means nothing but this, and then eta x t1 eta y t2 it can just be rewritten in this form. So when they're uncorrelated, you basically have the following statement. When you look at the product the expectation of the product, you can separate this into two terms: expectation of the first term times the expectation of the second term. Actually, you're allowed to do this when random processes are uncorrelated. We saw similar expressions, by the way, when we were talking about random variables. So you can do this if you have two things that are uncorrelated. Also, this is something that you're allowed to do when we have two random variables or two random processes that are independent too. Then it actually brings us to this next remark. So actually, could we actually generalize this? Could we say the following? If we have two random processes that are known to be independent, can we conclude that they are uncorrelated? So does independence imply uncorrelatedness? And then you can ask the second question, does the implication also hold in the other way around? So does uncorrelatedness imply independence? So now I'd like to answer this question in your minds. I can hear you say independent implies uncorrelatedness, but not the other way around. So this is exactly the way it works. So let's see why. If you just remember the independence definition, so for two random processes to be independent, so if you are able to call them independent, it means that any random vector x and y that you form in this way, no matter how many random variables you plug in, they have to be independent random vectors. Now, if you just think about when you have the right to call two random processes uncorrelated, you should just be able to do this separation, actually do this decomposition. So uncorrelated implies only two random variables. You look at x at a single value t1 and you look at y at a single value t2. So it's actually the same as it's as if you took a single random variable x t1 and y t2 in here. Of course, if the two random processes are independent, this first random variable will be independent of the second random variable, right? X of t1 and y of t2 will be independent random variables. It's actually, the concept of independent random process is actually much stronger than this. So the moment where you are sure that xt1 and xt2 are independent random vectors, so you're allowed to do this decomposition, so you can verify that they're uncorrelated. So if we just summarize what we should write here, so for two random processes, x of t and y of t, so if x of t and y of t are independent, this implies that x of t and y of t are uncorrelated. However, the implication does not work in the other way around. Uncorrelatedness does not imply independence. So, so in this way, it won't work, but in this first way, it will be fine. So this is a classical result that we also saw earlier. Okay. Now, then you can also similarly generalize the definitions of orthogonality. So the random processes are said to be orthogonal when the expectation about, so our x1 t1, our xy t1 t2 is basically this expression. So if this expectation is equal to 0, however, this should hold for any t1 and t2, then you say that the random processes x of t and y of t are orthogonal random processes. Straightforward generalization of the concept of orthogonality for two random variables. The next definition we have is jointly wide-sense stationary random processes. So when do you call two random processes x of t and y of t jointly wide-sense stationary? First of all, you're talking about joint wide-sense stationary. So first of all, each one of them should be wide-sense stationary individually. So the first condition is necessary. X of t should be wide-sense stationary and also y of t should be wide-sense stationary. However, there's more than that. They should be jointly wide-sense stationary, so there's some joint property that they should have together, which is the following. If you look at the cross-correlation function, Rx, y, t1, t2, remember, in general, this is a surface, right? This is a function of the two variables t1 and t2. However, if you can write this as a single parameter, that is, if you can write this as Rxy of tau, so a single parameter tau, tau is the difference of T1 and T2, then when you have these two conditions, then you say that these random processes are jointly White-Sun stationary. Okay, so this is going to be the end of the definitions about two random processes. So let's look at this very simple exercise. So we are asked to show that for jointly White-Sun stationary processes, remember, jointly White-Sun stationary means that the cross-correlation function is a function of tau. So what we are asked to show is that not only the cross-correlation function should be a function of tau, the time difference, but also the cross-covariance function should be it should be possible to write as a function of only the tau parameter, the difference between T1 and T2. So this is a simple exercise. So let's go through this. Okay, so here we have green one again. Okay, so let's write down the cross-covariance function, Cxy T1, T2. Again, remember what we're trying to do is we assume that the two processes are White-Sun stationary, and we are trying to show that this function of T1 and T2 can be written as a function of only tau. So let's start from the general expression. So we can write this in terms of the cross-correlation function Rx1, T1, T2 minus the mean functions. Eta x evaluated at T1 times eta y evaluated at T2, and if they're complex, we don't forget the complex conjugate sign. So what do we have? Now, our assumption is that x and y were jointly White-Sun stationary. So we know already that this first term, Rxy T1, T2, how can we write this first term? If they are jointly White-Sun stationary, this should be a function of tau only, right? This was the second condition for jointly White-Sun stationary. So this is a function of tau. And what about these two? Again, what is my purpose? My purpose is to show that I can write this thing as a function of tau only. So this first term is fine. What about the next two terms? So can I simplify this actually? Eta x of T1. First, it would be good if this was a constant, right? So do I have the right to state that this is a constant? Actually, I have, because why? If x and y are jointly White-Sun stationary, remember the definition. So if they are jointly White-Sun stationary, each one of them should be, first of all, individually White-Sun stationary, right? So if x is White-Sun stationary, it should be stationary in the mean, which means that this first term should be a constant. And it similarly holds, the same thing holds for y. So if y of t is a White-Sun stationary process, it should be stationary in the mean. This first term should be a constant. So what do I have here? First, a function of tau, then minus a constant times a constant. So obviously the second part is a constant. So the overall expression we have here is a function of tau. This is a function of tau, so I could maybe just simply call this as Cxy of tau, because it does not depend individually on T1 and T2, the whole expression. It only depends on the difference tau between T1 and T2. So this was our purpose. So this is the solution to this last exercise. So this first topic, the topic of two random processes, was kind of full of definitions and properties and remarks. So we will keep this for a moment, but then later on, I guess, especially when we study LTI systems, LTI stable systems, now we will typically have cases where x of t is a random process that enters an LTI filter, and the output process will be y of t. and then we will see how these two things are related. So then I guess most of these concepts will be useful. So let's keep them in our notes for the moment, so they will come back some time later. Okay. All right. Now the next concept is ergodicity. Okay. So what is this ergodicity about? So let's say that you're in an application, you have some random process x of t that you would like to deal with. For instance, it could be some signal that you want to process, and at the output you might be wanting to obtain another process, another type of signal. Or so it would be basically a filtering application. You have an input signal which is stochastic, and then at the output you want to have some signal that's structured in a certain way. Or you might be trying to do things on your original signal, like enhancing your signal, denoising, removing noise, or maybe predicting future values of your signal, and so on. So if you're in such a situation where you want to apply some kind of operation on your input signal, like you would like to design a filter or something like that, and if you have somehow decided to model your input signal as a stochastic process, a random process, then very often in most of the tools, what you need to know is some statistical properties of your input signal. So the most immediate statistical properties that you will need in order to design some filter or some kind of operation on your signal is the mean function and the autocorrelation function. These are two immediate things that you have to know about your signal. So when you know the mean function and the autocorrelation function, you can already design some filters. You can do things like predict future values of your signals and so on. So these are more advanced topics on signal processing, but it is possible to do. However, there's a slight problem in here. So assume that you're an engineer. You have an application where you would like to design some kind of filter on your input process. So you say, okay, I'm modeling my input process as a random process. Very good, but then nobody gives you the formula of the random process, right? You have some kind of data, some signal, and you don't know the mean function, you don't know the autocorrelation function theoretically. Then what you have to do to be able to design your filter is you have to estimate the mean function and the autocorrelation function. Then how can you estimate such a thing actually, just from just by observing your data? So you could actually maybe put this question in a more structured format. Let's ask the following question. So let's say we consider a wide-sense stationary process x of t. The question is, would it be possible to estimate the mean function, which is a constant in this case if it's wide-sense stationary? Would it be possible to estimate the mean of this random process and also the autocorrelation function of this random process with limited amount of information? Now, what is that amount of information? The deal is that you should be able to estimate this by observing only a single realization of the process. So in other words, the picture will look like the following. So you have your random process, you have a certain kind of data. So you have your random process x of t. The situation is like, okay, you would like to take this x of t, your input signal, maybe pass it through an LTI system or some filter or something. So there's some system that you want to design so that you get some kind of output. But then to be able to design this filter, you have to know the statistical properties of this. You have to know the mean. So you would like to know eta x, what is the mean value of this random process, and what is the, assuming that this is wide-sense stationary, what is the autocorrelation function, Rx of tau, of this random process. So if you know this, let's say that you're able to design your filter. However, in practice, you only have some observations of your data. So let's say that you have only a single realization of the random process, okay? Just have the signal, a single realization. And whatever you do, you have to do this with your single realization. So if you'd like to estimate this or estimate that from your data, the only thing that you're allowed to use is a single realization of the random process. In real life, nobody actually gives you the mathematical expression for your x of t. Now, the question is this actually. Can we find the mean function, the mean value, and the autocorrelation function of the random process using only a single realization? So is it possible to do this? So for some random processes, it is possible. For others, it is not. So this is the topic that we will study right now. So let's maybe ask the following question. Let's say that we can assume that our random process is such a random process that it's possible to estimate the mean function. Now, how would you do that actually? What would be your first guess? So somebody gives you a single realization of your random process. So well, maybe first, before discussing a single realization, let's maybe visualize our joint or our White-Sands stationary random process. So let's say that your random process normally has some realizations like this. So this is a realization, this is another realization. So this is a random variable that you obtain when you look at your random process at some t1, and then you have another random variable when you look at your process at some t2, and so on. But if you have a random process that is White-Sands stationary, you know that the mean function of your random process is constant. So let's say the mean function is this straight line, right? This is a constant, eta x, constant value. This is the mean of your random process. So what you would like to first do is find this mean value, the mean of the random process. But then how can you do that if you have only a single realization of your random process? So let's say the only thing you have is this. Somebody gives you a single realization of your random process. This is the same random process, x of t. Let's say that you have it up to some time instant capital T, okay? You have this observation and you're trying to guess what the mean of your random process is. So what would be your first guess? So if I give you the signal, if I ask you to estimate what this is, how would you do that? By using only this signal observation. Now, probably most of you would guess the answer. The thing that we should do is take the time average of this, which would be a good guess, right? So basically integrate this single observation, single realization of the random process. So take integral from 0 up to t, and then to find the average value, the time average, just divided by t. So this would be our this would be a good guess for estimating eta x. So if you just try to write this mathematically, so a good attempt to find an estimate of eta x is this time average. So you're integrating between 0 and t your random process, but don't forget, now I still prefer the notation x tilde of t. However, we should keep in our mind that this is not the mathematical object of a stochastic process anymore. This here in this integral, this represents a time function, a single realization of the random process. Okay, so just check. This is actually the thing that I just drew here. So this single realization. So we integrate this between 0 and t, and then we normalize by 1 over t so that we get an estimate actually. Now, we still haven't answered the question whether this estimate is anything close to the actual mean of the random process eta x, but this is the best of what we can do with a single realization. Take the time average. Now, if you are able to observe your process until the time instant t, capital T, now you would take this integral between 0 and t. Now, of course, as you can guess, the longer you observe your random process, the more data you will have. and then your estimates will probably get better and better. So in the limit case, if you just think that you're able to observe your random process sufficiently long by taking a capital T value that is sufficiently large, then the best estimate that you can get in this way is obtained by taking the limit as t goes to infinity. So if you just look at this, we consider this estimate, which is the time average of a single realization of our random process. We take the limit as t goes to infinity. So we observe our random process for a wider and wider time period, and then we integrate and we normalize by dividing with t, and then we look at what this limit happens to be as t goes to infinity. So this is the best thing that you can obtain from a single realization of a random process. Observe your random process for a sufficiently long interval. So actually observe your random process, your single realization of the random process at an infinite time interval, and then integrate and divide with time interval. So take the limit. So this thing we will call as an estimate of the mean of the random process. So this thing is going to be called as eta x, however, with a hat, so eta x hat. So usually in estimation theory, whenever you try to estimate some entity, you put a hat on top of it. So the question is, when this eta x hat equal to the actual eta x, the actual expectation, the actual mean of your random process. So for some random processes, when you do this calculation, it actually converges to the actual mean, the mean of your random process. But for some other random processes, this estimate will not be a true estimate, so it will not converge to the actual mean value of your random process. So random processes that have this property, where this estimate actually is a good estimate, it converges the actual expectation of the random process. So for random process having this property, we give them a special name. We say that such random processes are ergodic in the mean. So again, what is this definition? When I have a random process x of t, which is white sense stationary, so this is one assumption I make on my random process, I say that my random process is ergodic in the mean if this estimate obtained by taking the time average of a single realization of the random process is actually equal to the mean of my random process. So such random processes are called ergodic in the mean. Okay, now again, just a visualization of these two concepts they don't have to be equal by default, by the way. Some of you might be confused and you might think, but in any case, wouldn't they be equal anyway? So one is the average value of the random process, the expected value, the other one is the time average. Aren't they equal by default? No, the answer is no. So these two concepts are different. The first one, the mean of the random process, this is equal to the expected value by looking at your random process single time instant t. So you're actually looking at this random variable or another random variable, so you can do this for at any t value. So for any t value you get a random variable. So all these random variables have an expected value, and for white sense stationary processes, this expected value will turn out to be constant, right? So expectation of x of t, we just denote it with this single symbol, eta x. But eta x here means the expected value of this random variable that you obtain by looking at your process at a single time instant t. So this is what it represents. In the other case, the estimate, so let's say that you relate, so you just took this integral and multiplied with 1 over t. So this gave us the estimate of eta x with a hat. So this thing is not related, it's not obtained by looking at the random process at a single time instant t, right? It is obtained by looking at the random process at a very large interval of time instance. So here, in this estimate, you have the contribution of the observation of the random process obtained at many time instances, infinitely many of them. So one is a single random variable, the expectation of a single random variable, The other one is the time average. So these are conceptual different things. But if your random process is a nice one called an ergodic random process, then these two things are equal. So it's a special case when these two things are equal, actually. When this eta x is equal to eta x hat, then this is a special situation that we call ergodicity in the mean. Okay, now now here is some good news. We might wonder, is this limit easy to calculate or not? So the thing is, in the special case where your random process x of t is periodic, so let's maybe make it more explicit what we mean by a periodic random process. If your random process is such that the realizations of your random process are periodic functions, let's say with some period t0, then you don't have to go through this indefinite integral. So it's sufficient to look at the integral, calculate the integral over a single period only. Okay, you just have to integrate your random process between 0 and the period t0, and then take the normalize by the length of that period, so multiply by 1 over t0. So this integral is going to be the same as this one. So eta x hat is obtained in this way if you have a periodic random process. So the calculations get easier. Then another remark that we have is the relation between stationarity and ergodicity. So first of all, would it be meaningful to talk about a random, to discuss whether a random process is ergodic or not if your random process is not stationary? So if somebody gives me a random process that's not stationary, and if they ask me, is this a random process ergodic, is this a meaningful question? So this is the first thing we should discuss. So if you just imagine what's happening here, let's just visualize a random process that's not stationary in the mean. So it means that the mean function of the process is not constant. So possibly some realization of your random process might look like this. And then another realization looks like this. And then another realization. So imagine that in the realization of your random process, if you just draw the mean function is not constant. So it's a function that changes with time, maybe increases with time or decreases with time or something like this. So the mean function is variable with time. So would it be able to take such a random process and then try to take the time average, like take a single realization and integrate and then normalize by t and then try to get this value? So obviously this wouldn't make sense. So to be able to discuss ergodicity, you should first have stationarity. So if you have a random process that's stationary in the mean, so that the picture does not look like this, but it looks like this, then you can, after that only, you can discuss whether your random process is ergodic or not. But if your random process is not stationary in the mean, then the question of whether it's ergodic or not does not make sense. So ergodicity is not defined actually for non-stationary processes. Okay, so here's an example that illustrates ergodicity in the mean. So we consider a random process x of t. So here you have a sinusoidal random process. So it has an amplitude a. So a is a fixed variable, so it's a deterministic variable. So omega 0 is the frequency of your random process. So where does the randomness come from? It comes from the phase of the process. So the amplitude is fixed, deterministic, frequency is fixed, deterministic. Only the phase of the random process is random. So we have this random process. The question is whether this random process is ergodic in the mean. Now, maybe one thing that you might ask for attempting to show this ergodic or not is this random process stationary first? So why not like this? Okay. So actually, this is an example we discussed before in class. So I guess in section 3 I solved the version where theta was uniform distributed between 0 and pi, and then this one was left as an exercise, so hopefully you solved it. So the answer was that this process is actually white sense stationary when theta is uniformly distributed between 0 and 2 pi. So this should first be our starting point. Actually, we should first verify the white sense stationarity. So so let's just note that we showed before that x of t is white sense stationary, and actually we showed that the mean function is actually 0. The mean function is constant because it's white sense stationary, it's equal to 0. So what we should now check to discuss, to verify ergodicity, is that we should check whether the time average estimate of the mean, so eta x hat, that we obtain by taking the time average of the random process, so is this entity equal to the actual mean of the random process eta x? So this is what we should check. So okay, so the calculation is actually straightforward. So let's first find what this time average estimate of the mean is. So so eta x hat is obtained by taking this limit. So as t goes to infinity, 1 over t. So we integrate between 0 and t our random process x of t dt. Okay, here's just a note. I know that you're not used to seeing random things inside an integral, right? Because we usually have, I don't know, joint density functions and things like that. So we don't usually put random things inside an integral. So this case is different. We usually should think about a random process here. So you are integrating something random in here. However, be aware that we are talking about a single time function here, because we are talking about the single realization of our random process. So a fixed function. So if you're uncomfortable with this randomness in here, you could just simply erase this tilde sign, right? Some people prefer to do that. So I prefer to keep this tilde sign in here because this thing is, well, in estimation theory, usually you treat this thing as a random variable. This is called an estimator. So for technical reasons, I prefer to keep the tilde sign in here. But if you're uncomfortable with this, you could just erase this one. Okay, no big deal about that. So okay, let's calculate our integral. So limit as t goes to infinity, 1 over t. So what we have is 0 to t. Let's just write down the expression of our random process. So we have a cosine omega 0 t, I'll just continue the parentheses in here, plus theta dt. Okay, so the randomness comes from this phase term. So if you just evaluate the integral, so again still, let's copy limit as t goes to infinity, 1 over t. So the cosine will be integrated as sine, so it will go out as a over omega 0 because of the omega 0 t term in here, a over omega 0 sine of omega 0 t plus theta between 0 and t. Now again, if you're, well, let's maybe discuss about the role of theta in here. So remember, we are integrating a single realization of our random process. So whatever realization I have, now you go back to the question, my random process is defined in this way. So the only randomness comes from this phase term theta. But here we're talking about the time average of a single realization. So in that single realization, random variable theta takes a certain value. So if you want, you can go back to all the sample space things. So I have a random experiment. I obtain an outcome of my random experiment. So this theta, the phase term, has a certain value as the outcome of that random experiment. Let's say pi over 2, okay? Theta is pi over 2. So this is the outcome that I had. So I have fully the information of my random process. My random process will be, in that case, a cosine omega 0 t plus pi over 2. So theta is fixed to a certain value because I'm talking about a single realization of my random process. So here I prefer to keep theta as constant. I'm sorry, I prefer to keep theta in the random variable notation. However, be aware that since we are talking about a single realization of a random process, this thing has a certain fixed value, somewhere between 0 and 2 pi, but something fixed. And the integral that we are taking is over time. We are integrating over t, okay? So if this thing is getting you confused, it's all fine to just erase this and then erase any randomness in here, erase this one and that one, and then continue the integrals. It won't change anything. But again, for technical reasons, I prefer to keep this as a random variable. Okay, now back to our calculations. So let's write the explicitly the result of the integral. So this is equal to limit as t goes to infinity, 1 over t. So if you just evaluate the integral, so you get a over omega 0. So we evaluate between capital T and 0. So here's the first term. And if you just put in t is equal to 0, you will get sine of theta. Okay, now what was this again? Going back to the previous slide, this was our estimate of the random process, the time average estimate of the mean function. So let's just write it. So this is our estimate for, oops, what's wrong? So this is our estimate for eta x. Okay, now the question was again whether this eta x hat is equal to the actual mean function, identically equal to 0. So we should check whether this eta x bar is equal to 0. So if you just stare at this integral, well, it's not an integral, but if you just stare at this expression, we're wondering what happens to this expression as t goes to infinity, right? So again, theta is something random. Normally it's something random, but since we are talking about a single realization of our random process, theta is just a value, some value between 0 and 2 pi. Now if you just look at this term, you have sum of two signs. So this is the first sine term, this is the second sine term. So the sine function is bounded, right? It changes between between -1 and 1. So here it gets some constant factor, but obviously this second term in here is bounded. It has a finite value, no matter what t is. So no matter how large t grows, or no matter what's the value of theta, the second part is always bounded. So let's write this down. So this is bounded for any value of theta and also for any t, for any capital T. No matter if t grows to infinity, this second term will always be bounded. So now what you have here is a finite term, finite and bounded, and you're dividing it with t, and t goes to infinity. So what will be the result of this limit? It will come out as 0. You're dividing something bounded with infinity, so you get 0 in the output. So since now, if you compare the time average of the mean and the actual mean, we see that they are both equal to 0. So since these two values are equal, then we conclude that our process is ergodic in the mean. So x of t is ergodic in the mean. Okay. If you have any questions on these examples or anything about the course, well, I'll discuss it at the end of lecture, but don't hesitate to contact me. You could just put a comment below the in the YouTube page, just pointing to which second of the video, which moment of the video you're talking about, or you could just email me, or I think Melek Hoca is creating a WhatsApp group, so you could just post your questions out there. So don't hesitate to ask me questions. Okay, so this was this first example about ergodicity in the mean. Now, second example, let's look at this one. So let's consider this random process defined in the following way. So x of t is equal to a. So a here is a random variable. So x of t is constant. It's equal to this random variable. It takes this value a the whole time. And then what about the distribution of the random variable a? A is actually determined by a coin toss. So a can take only two values. It could be either +1 or -1. So we're just flipping a coin, and if the coin is heads, a takes the value 1, and if the coin is tails, a takes the value -1. So a very simple random process defined in this way. Now the question is x of t ergodic in the mean? Okay, let's look at this one now. Now, again, let's just remember that to be able to discuss, even mention ergodicity, we should first have stationarity. So let's first check if x of t is stationary in the mean, so that it makes sense to talk about the ergodicity. So maybe let's first just visualize what our random process looks like. So let's draw some realizations of our random process. So realizations of x of t. I'm getting better at drawing curves with this virtual whiteboard thing. Okay, so our random process takes the value a, so it's either +1 or -1, right? So actually our random process has only two realizations. It's either -1 or +1. Now, first question, even before ergodicity, is this process stationary in the mean? Let's first look at that one. So let's look at the mean function of our random process and x of t. So what is the mean function of this random process? Well, at any t random process, the random variable x of t is a, so it's either -1 or +1. So obviously the expectation of this random variable is 0. But if you do it for all t, you will identically get some function equal to 0. So the expectation of x of t, so the mean function of this random process, is equal to 0. So it's constant, it's equal to 0, so we already verified that x of t is stationary in the mean. It's stationary in the mean, so now we have the right to talk about ergodicity. Since it's stationary, we can ask whether it's ergodic or not. So let's look at that now. So to find out whether x of t is ergodic or not, it's actually enough to look at the two cases. Since our random process is either equal to +1 the whole time, or it's equal to -1 the whole time. This is case 1, this is case 2. So let's look at what our estimate of the mean function will be for both cases, right? So we need to look at two cases. So the first case is when, I don't remember if it was heads or tails, but the case when the random variable a is equal to 1. So let's look at our estimate, time average of estimate of the mean. So remember, what was this? We were taking our observation, a single observation of the random process, integrating over whole t, so x of t, I'll start from here. So we integrate our random process between 0 and t for a sufficiently long time. Remember, this is a single observation of our random process. We are integrating between 0 and t, normalizing by t, and looking at this at a sufficiently large interval. But we're talking about a single realization of our random process here. But we know in which case we are. We are in the case where a is equal to 1. And when a is equal to 1, as you remember from the previous page, when a is equal to 1, our random process is identically equal to 1 everywhere. So what we have is that in this first case, x of t will be equal to 1 everywhere. So let's look at this integral now. We are integrating one function, constant function 1, between 0 and t, and dividing by t. But for any value of t, actually, this integral will come out as 1, right? If you let t go to infinity, I'm sorry, this is infinity, not 0, obviously. So even when you let t go to infinity, this integral won't change, so it's going to be equal to 1. So our estimate of the mean is equal to 1 for this first case, the first realization of x. But then the question is whether this was equal to the expectation of the random process, the mean function of the random process. The mean function of the random process is 0. So if we are in this first case, this is not equal to 0. So this is not equal to the actual mean of the random process. Now we already observed from here that the ergodicity fails actually. So still, let's look at the second case to be complete. The second case is where a is equal to -1. So if you just evaluate the same integrals, basically you will have -1 here instead of 1. So you will have a similar integral. So the time average estimate of your random process will come out as -1. And this is not equal to the mean value of the random process. So what we conclude from here is that no matter which realization I take, so I might take this first realization or the second realization, no matter which one I take, in both cases, the estimate of the mean that I obtain is not equal to the actual mean. So the ergodicity assumption fails for this random process. This random process is not ergodic in the mean. So we could just note that for both realizations, we have that the estimate of the mean, the time average estimate of the mean, is not actually equal to the mean. So we conclude that x of t is not ergodic in the mean. Although it is stationary in the mean, though, let's also note down this interesting observation. Although it is stationary in the mean, okay, so this is a very nice example where ergodicity does not come by default, actually. Your process might be stationary in the mean, but it does not mean that it has to be ergodic in the mean. These are two different things. This process is perfectly stationary in the mean. Its mean function is 0 everywhere, but no matter which realization of the random process we take, we can never estimate the mean correctly with a single realization of the random process. It would require to have more than one realization of the random process. So this process is not ergodic. Okay, now let's let's go back to our notes. Okay, now what we have discussed so far is the ergodicity in the mean. Yeah, remember our original question of interest. We were wondering if we can find the mean function and the autocorrelation function from a single realization, right? So we have looked at the question, when can we estimate its mean from a single realization? The answer is you can do this when your process is ergodic in the mean. Now we have to answer the second question. When can we estimate the autocorrelation function, Rx of tau, of a Weissenstein random process by observing only a single realization of the random process. Now we have to answer the second question. So what we will be simply doing is that we will take this ergodicity concept, which we defined for the mean function, and we will extend it for the estimation of the autocorrelation function. So, okay. So, similarly to the estimation of the mean, we may also wish to estimate the autocorrelation function. So here, I would just like to, before jumping into this, the formulation, I would just like to give you some intuition about this. So, again, what are we trying to do here? We have a random process that is wide sense stationary. So, what we are ideally trying to find is this autocorrelation function of our random process. So what was this again? This is the expectation of, remember the definition of the autocorrelation function. I look at my random process, it's some t plus tau. Now I look at the random process, it's some t, conjugate sign if my process is complex. So this is the function that I'm ideally trying to estimate. I would just like to give you a visualization of, again, what this function would represent. So let's consider some realizations of our random process x of t. So here is one realization. So here is another realization. So what we are doing here is that we are looking at the random process at some time instant t, and some time instant t plus tau. So let's take some t in here. So I get this blue random variable, which was unnecessary to say because I will still use the blue color for the next one. So let's look at the random process at some t plus tau. So I get the second random variable, t plus tau. So the time difference between these two time instances is tau. What this autocorrelation function tells me is, tells me the following: take this random variable and take the second random variable, multiply them, just forget about the conjugate thing, let's say they're real, multiply this first random variable and the second random variable and look at what expectation you get, okay? So, of course, obviously, as tau changes, this expectation expression will change with tau. And this is the function that we are ideally trying to estimate. Now, if you know your random process analytically, let's say in a mathematical way, of course you can calculate this expectation and find out what this function is. But then again, remember, we are in a setting where we don't have any mathematical analytical expression about our random process. So what we have is actually, we have a single realization of our random process. So whatever we do, we have to obtain it from a single realization. So we are given a single realization. So let's say we have something like this. And we are trying to find out, we're trying to find an estimate for our autocorrelation function. So what is the best thing that we can do actually? Again, remember, this was about the expectation of the product. So if you look at the random process at some t, and it's some t plus tau, so I can actually look at what this product is for this particular time instant t, right? I take this blue value and this corresponding blue value, I multiply them, and then I have some data. This gives me one data about towards the estimation of the autocorrelation function. But then only one pair is not sufficient, right? I have to make sure that I get this as correctly as possible, actually. So what can I do? I only have a single realization of my random process. Well, I could look at how this thing changes with theta. I'm sorry, with Oops, that was a bad arrow. Okay. Here is a nice arrow. Okay, I would like to look at how this thing changes with tau in general, but I can't use any other realization. This single realization is all I have, but then I can make the most of it, right? So what if I look at this at another t and t plus tau pair? So let me take this t at this red point, and then by keeping the same time difference tau, let me take the corresponding t plus tau. So I keep the same tau in here. So this gives me another pair. So I could actually do this as long as I want. If I have a sufficiently long observation, I could just take a green pair in here. But in each, I'm kind of like probing my signal to take data from it. I take these blue values, I take these red values, I could take some green ones in here. They would all have the sign difference tau. And if I take the average of this, average of what? X of t times x of t plus tau. And if I do this for any possible t value that I have just by sweeping all the possible value of t, again, I'm using only a single realization of my random process. So this could actually give me some estimate for the autocorrelation function, right? So it actually works as follows. So what we would like to do is we look at x of t, or you could write it the other way around, x of t plus tau multiplied with x of t. So the product of these two blue values for this t value, or the product of the red values if you take t here. So actually consider all possible values of t that I have. So let's say that I can observe I have the observation of my signal until some capital T value. So I consider this product between 0 and capital T. I look at all the pairs that I obtain, and I'm actually trying to take the average value of this product, right? But how do you do that averaging? Because T varies continuously, you just integrate this. And then since you would like to take an average, you then normalize by T. So this thing is actually going to be an estimate for this the actual autocorrelation function. So we will be calling this Rx of, I'll just erase this first one. So this thing is going to be an estimate of our autocorrelation function. So since it's an estimate, I put a hat sign. And since this involves the time averaging over the interval 0 to t, so capital T is some parameter that I have, I put a t just to remember that I have this finite time average. Now, if we go back to the notes, so this thing is an estimate. It's a good candidate for an estimate of the autocorrelation function. Now, obviously, if you have a longer observation of your signal, means a larger t value, that's going to give you a better estimate, right? So in the limit, the best of what you can obtain from such an estimator is the limit case, as capital T goes to infinity. So as t goes to infinity, we look at this limit, just this expression, we take the limit as t goes to infinity, and we just give it the name Rx tilde of tau, however, with a hat sign. Because this thing is supposed to be, hopefully, it is going to be an estimate of our autocorrelation function. Now, the good question is, can I claim that the estimate of the autocorrelation function that I obtained in this way by taking the time average, can I claim that this is actually a good estimate for the actual autocorrelation function? The answer is, for some kind of random processes, yes. And whenever I can do this for a random process, I call that process ergodic in the autocorrelation function. So here is the formal definition for that. So a White station random process x of t is said to be ergodic in the autocorrelation function if this limit obtained by taking the time average of the product x of t plus tau x of t time average over 0t as t goes to infinity. So if this estimate is equal to the actual autocorrelation function in the limit as t goes to infinity, then we say that that process is ergodic in the autocorrelation function. So some wide-sense stationary processes have this property and some of them do not. When they have this property, we say that they're ergodic in the ACF. Now again, as before, to discuss whether a process is ergodic in the ACF or not, we first have to start with stationarity. So we first assume that our process is wide-sense stationary. So if somebody gives you an arbitrary random process, if they ask you whether it's ergodic, the first thing you should check is if it's wide-sense stationary. Then if it is not wide-sense stationary, then the question is meaningless. If it is wide-sense stationary, then you would look into whether it's ergodic in the ACF or not. Okay, another remark, when the realizations of x of t are periodic functions with period t0, then the estimate, remember this estimate, we have to take this integral between 0 and t, and then take the limit as t goes to infinity, so you have some calculations to make. But in the simple case where x of t is periodic, you don't have to evaluate an infinite integral in here. It's sufficient to evaluate the integral over a single period. So t0 would be the fundamental period of your random process. So it's enough to take this time average over a single period. Now, well, if you're wondering why this is the case, let's just draw the following picture. So you have a random process, x of t. So I'll try to draw a periodic random process, so something like a sine. Let's see. So here's a period, and here is another period, and so on. So let's say that this is, it was not bad, no? This is the fundamental period t0. So remember, what you're trying to estimate is you take these pairs that differ by tau. Let's say you have this black pair, and then let's take a red pair. Well, as t changes, these pairs change. So what your integral says is, I'm sorry. So you take the product of these random variables, then you take the product of the red random variables. So you do this for all t values. But if your random process is periodic, now if you just complete a single cycle, now if you come back to here, now oops, the black color is what I need. Okay, if you look at these two random variables in here, the black ones, they're going to be the same, right? And again, if you continue increasing your t, you will come back to this, to the green random variables, which will have exactly the same values as in here. So instead of doing this over one period, 2 periods, 3 periods, and infinitely many periods, it's actually sufficient to evaluate this integral only between 0 and up to t0. So this is the, if you just look at the integral between these green lines, then you don't have to evaluate the integral over the whole real line. It's sufficient to look at it over a single period, because the values will start repeating themselves after a while. So this is just a note to make the calculations, it's a calculation trick actually, to make the computations easier. Now another remark. So something interesting happens when the time difference parameter tau is taken as 0. So let's look at what we have. So the time average estimate was in this expression. So we are looking at this expression when we take tau is equal to 0. So you'd get x of t from here and x conjugate of t from here. So this is the, well, looking at the limit case. So x of t, x conjugate t multiplied and integrated. But then this multiplication is, since we're looking at it at the same t value, this product is nothing but the magnitude square of the random process at t. So actually this thing has a meaning, it has a physical meaning. So if you just look at this, the integrand, x of t square, So this is nothing but the instantaneous power, right? If you just think about, if you just, I don't know, draw the analogy, if you think of x of t as a voltage value, some random voltage signal, this is going to be v squared. So it's related to power. So this is called the instantaneous power for certain t. But then what we are doing in this calculation is we are looking at this for all possible t values, integrating and dividing by t. So we're actually looking at the average value of the instantaneous power. But then this is nothing but the average power of the random signal, right? It's a time average. But if your random process is a special one, so namely if your random process is ergodic in the ACF, then you have this nice equality. So our x of 0, our x hat of 0, so the estimate at 0, will actually be equal to the true autocorrelation function, which is the expected value of x of t magnitude squared. So all these expressions are the same, and they are all called the average power of the process if you have a wide-sense stationary process that's ergodic in the ACF. Okay, it's just a note that to note that we give special name to the ACF when we evaluate that as at tau equals 0. Okay, now two more exercises, and then we will conclude this chapter. So let's look at the random process in the previous example. So remember this random process. We looked whether it was ergodic in the mean or not. So let's now ask the question: is this random process ergodic in the ACF? The random process with this random phase theta. Theta is uniformly distributed between 0 and 2. So I'm in page 9. Okay, so again, it was a homework exercise to show that this was wide-sense stationary. So I'll just write the expressions for the autocorrelation function. Here you can verify. It's a quite easy exercise to do. So let's just note. So we showed before that the autocorrelation function Rx of tau was given by this expression. So a squared over 2 cosine omega 0 tau. Okay, the process was wide-sense stationary, so the ACF was a function of tau, and this was the expression. Now what we should do is to check ergodicity, we should check the following. So we must check whether the time average estimate of the ACF is actually equal to this true ACF, the actual ACF. Okay, so we just have to do the calculation. So let's go. Let's find out what the time average estimate is. So we'll just evaluate this limit. So as t goes to infinity, normalization by t. So this infinite integral x of, remember we are trying to estimate the autocorrelation function. So ideally we would be looking at the expectation of this expression. The expectation of this expression, x at t plus tau times x of t. But we can calculate the expectation theoretically, suppose. So we are looking at the time average. So this is the estimate of the ACF. However, if you just remember what kind of function we had, so this is a cosine function, right? Is this function periodic? Well, more precisely, this is a random function, it's a random process. But can we say that any realization of this random process, can we say that it's a periodic function? Now think about this. You take a realization of this random process, A is fixed, omega 0 is, they are fixed and deterministic anyway. But if you talk about a single realization, this theta random variable will have a fixed value, right? Because you fixed your realization. Theta is something, it's some phase angle. So this function is actually going to be a periodic function. So since this is periodic, now we can just use this more convenient formula. So since x of t is periodic, then you could just evaluate this limit. You don't have to deal with infinite integrals, indefinite integrals. You just have to, it's just sufficient to calculate this over a single period. So let's just look at this one and we will be fine. Now, what is this T0, by the way? If I give you this random process, would you be able to write down what T0, the capital T0 is? Well, here is the fundamental frequency of your process. So the fundamental period T0 will be nothing but 2 pi over omega 0, right? You remember this from 301. So, okay. Now, let's write down, let's do the calculation for our specific random process. So we are looking at it over a single period, single realization, single period. So our random process was a cosine omega 0 t plus theta. So we first look at it at t plus tau. So we get a cosine omega 0 t plus tau. And then the phase term. And then, so this is x of t plus tau. Then we have to write x of t, but x of t is a cosine omega 0 t plus theta. So a is already here, so we just put square to add the second a, and then write the rest of the term. So cosine omega 0 t plus our phase term, theta dt. This is where my whiteboard stops. Okay. I should change the settings, I guess. Okay, so the dt is here. All right, so now let's calculate this integral. Well, actually, we have the product of two cosine terms here. So cosine of something times cosine of another thing. You remember trigonometric identity, so if you just call this one A, the second one B, you have cos A, cos B. So it can be decomposed as cosine A plus B, and then cosine A minus B, so you add them, divide by 2. So if you just use that trick, you can rearrange the terms in the following way. So 1 over t0, so a squared, let's take it outside and let's divide by 2. That comes from the trigonometric identity. So 0 to t0. So now we will just write the first cosine term, which comes from the sum of this expression and that expression. So if you just sum them up, you have omega 0 t here, omega 0 t here. So you have 2 omega 0 t. Then you have 1 omega 0 tau coming from here. And then you have 1 theta coming from here, so it gives you 2 theta. And then, so this was cosine A plus B. Now we add cosine A minus B. So you have this term, you're subtracting this term. So omega 0 t will cancel with minus omega 0 t. And theta will cancel with theta. And the only thing you have will be omega 0 tau. So cosine omega 0 tau and that's it, dt. I'll just put curly brackets and dt. Okay, now if you look at this expression, now we are integrating the overall expression from 0 to t0. We are integrating it over a single period, actually. Now you have the sum of two cosine terms here. So the first cosine term you see in here, let's see what this is. We're integrating over t. So I could actually consider all of these as fixed things, right? Tau is something fixed, theta is random, but it's fixed anyway because I have a single realization of my random process. So the combination of omega 0 tau plus 2 theta, I could simply think about as a constant phase term. So the variation comes from this part. But if you see here, you have a periodic signal 2 omega 0 t. So actually, if you look at this within the time frame 0 to t0 in a single period, so since you have twice the fundamental frequency in here, it will make 2 cycles. So you have a cosine making 2 cycles, and you integrate this, it will come out as obviously as 0. So let's just note that this first term will vanish when integrated. So will vanish when integrated. And then you will be simply left with this second term, right? Cosine omega 0 tau. So if you just look at what this gives you, so now t was our variable. This is something fixed. It does not change with t, and you're integrating this fixed thing from 0 to t0. Fixed number integrated over a period will come out as t0 times that number. So we get the integral as 1 over, I'm just writing these constant terms, 1 over t0 a squared over 2. So t0 times cosine omega 0 tau. And these terms will cancel, so we'll be left with a squared over 2 times cosine omega 0 tau. So, okay, where did we obtain all these things? Remember, we were looking at the estimate of the autocorrelation function. We calculated all the integrals. We obtained this expression a squared over 2 cosine omega 0 tau. And then the idea was to compare this time average estimate of the ACF to its true value, but the true value was this. So if you just compare these two expressions, they're equal. So it means that the time average estimate of Rx tau is actually equal to Rx of tau. So this gives you the conclusion that this process is actually stationary in the autocorrelation function. So let's write this. So since Rx of tau, since the estimate of the ACF Rx hat of tau is equal to Rx of tau, and this holds for all tau, so these two functions are the same actually. No matter what the value of tau is, these two values are the same, which tells you that these are equal functions. So since this is equal for all tau, and also for any realization of the process, right? So again, what changed from one realization of the process to another? This value of theta is what changes between two realizations. But whatever realization I take, whatever theta value I take, I obtain the same result, right? Theta is not involved in this actually. So this holds for any realization of the process. So for all tau and for any realization of the process, then we conclude that x of t is a process that's ergodic in the ACF. Okay, so this is the answer of this first example. So let's also look at the second example, which is the last example of this chapter. So here we have a random process x of t. This is again a complex exponential. Its amplitude is fixed and deterministic. Its frequency is fixed and deterministic. Again, the phase is random in here. So theta is uniform distributed between 0 and 2 pi s. It's a similar example actually. So is x of t White-Sands stationary? Let's first answer this question. Then if yes, let's determine if x of t is ergodic. Okay. So okay. Now we should first answer whether this is White-Sands stationary or not. So let's first look whether it's stationary in the mean. So let's look at the mean function. So the mean function is the expectation of x of t. So if you just copy the expression for our random process, so it have a exponential j omega 0 t, and then you have some phase term theta. So I prefer to write this separately in here. The phase term is where the randomness comes from. So we're looking at the expectation of this expression to find the mean function. But if you just observe here, this thing is not random, right? This is time dependent but deterministic, so it would go out of the expectation. Then you're left, in the expectation, you're left with e to the j theta. But theta is uniform distributed between 0 and 2 pi, so its expectation of this term will be 0. So this comes out as 0. So the mean function is equal to 0, so this is a constant value, so we conclude that, first of all, our process is stationary in the mean. You could similarly look at the autocorrelation function to decide whether your process is stationary in the ACF. So then the idea would be to look at this. So we are interested in this expectation. We look at x of t plus tau times x of t. And in this case, our process really is complex, so we should not forget the conjugate sign. So we have, if you just write down the expressions, so x of t plus tau, you would have a e to the j omega 0 t plus tau. And then you would have, okay, there's also the phase term, sorry. So e to the j theta. So this is the first expression for x of t plus tau. And then you have the second expression, x conjugate of t. So you have similarly e to the minus j omega 0 t. And then the phase term. I prefer to write this phase terms separately for the following reason, that they will actually cancel very nicely, so that we don't actually have to take the expectation. By the way, let's just also add the, we should not forget here the randomness of theta. Theta is the only thing that's random here. So again, we were interested in calculating this expectation to find the autocorrelation function. So these two terms cancelled. So then the thing that's left to do is to see whether this comes out as a function of tau only. So let's see. So you have this first term that depends on t, but it will be cancelled with this one. So then you will be left with a square x e to the j omega 0 tau. So this is the ACF. But since this thing is constant, right? Actually, the only randomness comes from the theta. So theta is cancelled. So this thing is deterministic. So you could simply actually remove the expectations. You could simply erase the expectations, because the expectation of a constant is equal to itself. So this is what our autocorrelation function is. And indeed, it is a function of tau. So we have all the right to call this our x of tau, because it depends only on tau. It does not depend on t. So let's note that this is a function of tau. So what we conclude from this these derivations is that the mean of our process is a constant function, and the autocorrelation function of the process depends only on tau. So we conclude that the process is White-Sands stationary. So x of t is White-Sands stationary. Now, in the rest of the question, we were asked to find, well, is this White-Sands stationary? Yes, as we showed. And the next part is to determine if x of t is ergodic or not. So let's also do that. So the second part of the question is to see whether it's ergodic. Now, there are two things we should check. We should check ergodicity in the mean and ergodicity in the ACF. So to check ergodicity in the mean, we should find time average estimate of the mean. Remember, it was found by integrating, since our process is periodic, it's sufficient to integrate over a single period. So we integrate between 0 and t0. Let's write down the expression for our random process. E to the j theta dt. So again, this is a time integral. Careful, this is a random, this is the term that includes randomness, and we are taking a time integral. So if you look at this integral from the perspective of t, this is a constant term. You could even take it outside, and what you have here is a complex exponential, and you're integrating that complex exponential over a single period, so it will come out as 0. So the time average estimate of the mean is equal to 0. Remember, the mean function was also equal to 0, so things are on a good track. So we conclude from here that the time average estimate of eta x is actually equal to the mean function. So from this equality, we can conclude that x of t is ergodic in the mean. Okay. The second part that we should look at is whether it's ergodic in the ACF. Now, to do that, let's look at the time average of the autocorrelation function. So again, because of periodicity, we could just evaluate the integral over a single period. So from 0 to t0, we have x of t plus tau. So let's just write down x of t plus tau. So a e to the j omega 0 t plus tau e to the j tau, j theta. And then you multiply this with x of t conjugate. Then you have again a e to the minus j. Because of the conjugate, you have the minus j sign. E to the j omega 0 t, and then similarly you have the minus term, minus sign before the phase term, dt. So theta is random here. So again, the nice thing here is that these theta terms cancel nicely. So this will cancel with this one. So that when you evaluate the integral, you will have one over t0, 0 to t0, a square e to the j omega 0 tau d tau. But then, I'm sorry, not d tau, dt. Because this term that has this dependence on t in here will get cancelled by this term, so you will have only the term with tau here. dt. So you're integrating over t, but your expression does not depend on t, it depends only on tau, so that you have a constant integrated over a period divided by the period. It will just simply come out as itself. So a squared e to the j omega 0 tau. Now, this was the estimate of the ACF, Rx of tau. So if you remember, we previously derived the autocorrelation function. It had the same expression. If you just compare the actual autocorrelation function with the time average estimate of the autocorrelation function, they are the same. So we conclude that this is equal to Rx of tau. So since the time average estimate is equal to the actual ACF, then we conclude that our random process is ergodic in the ACF. So our random process is ergodic in the mean. It's also ergodic in the ACF. So for random processes that have these two properties, ergodicity in the mean and ergodicity in the ACF, it's a common practice to call these processes simply ergodic. So if somebody asks you whether a process is ergodic or not, you should check mean and the ACF. Okay, so just a little note about these derivations in case you would get confused. You might be thinking that we're actually doing always the same thing because integrals are actually similar. But just be careful here. So the similar terms cancel, but for the actual autocorrelation function, we're actually looking at an expectation. So this thing involves an integration, but the integration will be over theta, right? Theta is what's random here. Since theta is random, we are talking about an expectation, and if you were to calculate this expression explicitly, you would integrate over the density of theta. However, the other integrals that we used to find the time average of the ACF and the time average of the mean, they were over t. So from the perspective of these integrals, actually theta is something that has a certain fixed value because we are just interested in a single realization of the process in here. And the integration variable is t in here. So theta is like fixed and t is variable in the time average estimates, whereas in the other case, theta was random and the integration was over the variable theta. Okay, so these were the two examples that illustrated ergodicity. So this is going to be the end of chapter 3, ergodicity and stationarity and ergodicity. So we will finish this first lecture video here. So I guess you would have questions. So again, you could just post your questions under the video on YouTube, so it would be public in the public, meaning that only the people with the link can see it. So we could just discuss among ourselves. So other people in the class would also profit from your question. Or otherwise, I don't know if we have activated the forum on ODTÜ class. Otherwise, there's this WhatsApp group that's well, if you're looking at this video and if you're not in the WhatsApp group, just tell one of your classmates who would add you to the list. Otherwise, you could just email me and I'll take care of it. Or Melek Hoca. Okay, so I hope you have found this video useful. So any comments you have, you might have positive or negative feedback. I don't know if you have spotted any problems like my voice was not clear, or the writing was not clear, or I don't know, the resolution wasn't good enough, and so on. Just let me know. Otherwise, if you have found the video useful and if you like this, if you like us to continue this format, this is also a good feedback for me. So just tell me about your comments. So we are really in the experimental phase now, so let's try to figure out what's the best way for doing this online education thing. So thanks a lot for listening. So bye and see you in the next video.